So in looking at control of respiration, we'll begin with the neural control of respiration. As you can see on the figure to the left, there is the medulla oblongata of the brainstem, which is the part that houses the respiratory center. You also have up in the top of the pons, the pontine respiratory group. So in the medulla oblongata, you see first in the front, the ventral respiratory group, also called the VRG because it's on the ventral side. And toward the back of the medulla oblongata, the dorsal side, you see the DRG, the dorsal respiratory group. The dorsal respiratory group stimulates muscles that will cause inspiration or inhalation, and as we've learned, should be the diaphragm and external intercostals. As a little tip, if you're having a hard time remembering the difference between the function of the external intercostals and the internal intercostals, I remember the external intercostals begins with an E, so does elevate. They elevate the ribs for inhalation. The ventral respiratory group controls forceful breathing and breathing rhythm. So remember that quiet expiration doesn't use muscular activity. It only requires a relaxation of the diaphragm and external intercostals. It is largely a passive process. The ventral respiratory group, therefore, is not necessarily a control of expiration. It controls forceful breathing, which we've learned uses more muscular groups and also sets breathing rhythms. Now, that pontine respiratory group up at the top of the pons, as you see, may modify that rhythm set, which we'll talk about in a moment. So that rhythm is set by the VRG and can also, through that process, transmit impulses to the DRG, which regulates our normal breathing. So some definitions: we know that breathing occurs without conscious control. It's controlled there by that brainstem. That VRG sets the rhythm. Dyspnea is a feeling of shortness of breath. That may be a result of COPD, of many different things. And what we call with that normal breathing without conscious thought or control is eupnea, one of the most vital functions because it carries oxygen in and CO2 out, and where respiratory system works closely with the cardiovascular system. So this is an important flow chart to see how the DRG and VRG work together to control both normal and forceful inspiration and expiration. Notice normal quiet breathing is controlled solely by the DRG there at the back of the medulla oblongata, the dorsal respiratory group. It remains active for roughly 2 seconds and inactive for 3 seconds. We know when it is active, it is stimulating those inspiratory muscles, the external intercostals and the diaphragm, to contract. When they contract, they expand the volume of the chest cavity. That makes pressure in the lungs drop. When that pressure drops below atmospheric pressure, we can inhale 2 to 3 liters of air. If it is inactive for 3 seconds, that means that we just relax the external intercostals and diaphragm. It is a passive process, and because of surface tension of alveoli and the elastic tissue of the lungs, they go to their original position. So when we're normally breathing, the DRG is active. Now we can alter the rhythm of breathing. We can also have deep inspiration and deep expiration, and we're going to see that we'll start to pull in the VRG then. So if we look at figure B during forceful breathing, we still have the DRG controlling the external intercostals and diaphragm, which are always used, whether it's normal inhalation or forceful inhalation. But if we're doing forceful inhalation, in addition to the external intercostals and the diaphragm, we are also going to have to recruit some of those muscles that pull up those ribs 1 through 5, like the sternocleidomastoids, scalenes, and pectoralis minors. And then we're going to recruit our VRG to do that. So both the DRG and the VRG are involved in forceful inhalation. If we look at forceful exhalation, we only involve the VRG because that is going to use the internal intercostal muscles, your abdominal muscles, to force the diaphragm up. So forceful exhalation is controlled by the VRG. So that may want to be a summary you write down. Normal quiet inhalation and exhalation requires the DRG only. Forceful inhalation requires both the DRG and VRG, and forceful exhalation requires the VRG only. We can alter that rhythm set by the VRG due to cortical influences, which means our higher brain center, the cerebral cortex, can tell us we need to alter breathing. So we see here the person holding their breath underwater and one baby crying and one baby laughing. So we can obviously change the rate of breathing as needed, even though that rhythm is set under not under conscious control. So those higher brain centers, cerebral cortex, hypothalamus, and limbic system, which is our emotional brain, can all influence those things. Now, also influencing our breathing rate are chemoreceptors, and we should know what those are at this point, but they are just nerve receptors in our large arteries and also in our central nervous system that monitor the chemicals oxygen, CO2, and hydrogen. Largely, they monitor hypoxia, which is low oxygen, hypercapnia, which is high CO2, and acidosis, which is a high amount of hydrogen ions. Central chemoreceptors respond to those changes in chemicals in the cerebrospinal fluid. And peripheral chemoreceptors are in your aortic and carotid bodies largely, so in the blood. And they will detect these and they can alter rate of breathing because of that. So we see this is a negative feedback system. Hypercapnia and hypoxia, high CO2 and low oxygen. So if CO2 or hydrogen decrease below their normal range, the central chemoreceptors pick this up. They relay that information to the DRG, which triggers hypoventilation, so lower ventilation, so we retain more CO2 and bring it back into balance. The opposite, if we have a high amount of CO2, the central chemoreceptors detect this. We monitor the DRG. This figure says RPG, just using some different terminology, same as DRG. And hyperventilation means that our ventilation rate will increase. We will blow off more CO2, bringing it into normal ranges. Propriostimulation means that we have nerve receptors in our joints that monitor body positions. So if we start exercising before we build up too much CO2 and get low on oxygen, our body is going to increase ventilation rate in preparation because it knows the position of our limbs. The inflation reflex means that regardless of how deeply we breathe, we are not going to have excess lung overinflation because we have baroreceptors in our bronchial tubes that detect the stretch. So baroreceptors, just like the ones that are in our blood vessels, are in our bronchial tubes, and they know how the stretch is. So probably one of the only cases that we'd see something like lung overinflation is in scuba diving. If you take a deep breath while you're below atmospheric pressure and you hold your breath as you rise, that gas rises as you get to the atmosphere, and that could cause lung overinflation. But just from breathing heavy, as you see the person here that got done exercising, we probably wouldn't see this. So in our summary of respiration, your cerebral cortex, changes in arterial CO2 and hydrogen, as well as hypoxia, stretching of trachea and bronchioles are all going to be under control of cerebral cortex, chemoreceptors, central and peripheral, and stretch receptors. So they are going to have varied effects on ventilation. Notice that changes in the partial pressure of CO2 and hydrogen are controlled by the central chemoreceptors, monitored by cerebrospinal fluid, and arterial oxygen largely by blood, peripheral chemoreceptors. When we exercise, there are going to be noticeable changes in both our cardiovascular and respiratory system. Blood flow to the lungs increases because blood is going to have less time at pulmonary capillaries to pick up oxygen. So we say our pulmonary perfusion increases at the lungs in order to compensate for this during heavy exercise. So our oxygen diffusing capacity may increase threefold during maximal exercise. So there's a bigger surface area available to extract more oxygen as we need it for exercise. So in our big picture of respiration, we see external and internal respiration here. So at our pulmonary capillaries, we take in oxygen, give off CO2. At our internal or our systemic capillaries, we give oxygen, pick up CO2. So a little bit about pneumothorax. If the intrapleural pressure between the visceral and parietal pleura goes to 0, there is no longer a suction effect that keeps those lungs inflated, because we know that intrapleural pressure between those areas changes as lung volume changes in pulmonary ventilation, but it doesn't equalize with atmospheric pressure. So here we see a knife going in that figure on the right. If we equalize that intrapleural space with atmospheric pressure, there's no longer that suction, and it can cause a lung to collapse as the elastic recoil in the lungs pulls it back in. That is known as a pneumothorax. Things that can cause it could be a pleural effusion. That could be excess fluid. That may mean that there's something blocking lymphatic flow that builds up extra fluid. Could be a hemothorax, that blood is in the cavity. Could be air equalizing there in that region. So several things can also cause pneumothorax.